Alright, so this could be our notes on conservation of momentum. We've been talking about momentum already, and you should have a pretty clear grasp of what that is. And that's just the mass of something times how fast it's going, or its velocity. And it's just a measurement of those two things. We multiply them together, and it gives us a unit called momentum. And so far we've been looking at single objects, really. We've been looking at how much momentum a car has, or a truck, and it has so much mass, it's going down the road. How fast is it going? We just multiply them together and we get a number, and so on. And we also related it to force and time, and the change in momentum, so that's equal to change in momentum, and that's called the impulse momentum theorem. So we can see that from this equation that force and time have a relationship with the change in momentum. So both of these have something to do with momentum when it changes. So either the amount of time or the force determines how this changes. Now we're going to start talking though about something conservation of momentum. So it means it's conserved. And if you remember from conservation of energy or matter, that means that matter or energy cannot be created or destroyed. It's just transferred somewhere else. So an important part of this conservation of momentum is now we're talking about more than one object. We're talking about two or more. So it could be 3, 4, 5, whatever. And this equation kind of explains what happens when, or what happens with the momentum of objects when they interact. So if you remember, we watched a video on the pool. These guys were playing pool. So what happens if this ball is just sitting here, the guy shoots it? What's going to happen to the behavior of it? What's going to happen to both of these once this guy shoots this pool ball? Can we predict? Is there some way? Do these have movements, and will these two things move in a predictable way? And if you remember from the video, they will. And the initial equation for this, to understand this, is initial momentum, m of I, or P of I, momentum initial, equals momentum final. So it's conserved. So in the universe, at the hockey rink, wherever we are, if an object has momentum and it interacts with another one, the total amount of momentum they both started with at the beginning will be the same amount that they have at the end. The more fleshed out equation here is, so we know momentum initial, and we know it's two objects. So then we have, this is the first object, number 1. And the momentum for that is just mass times velocity. And then we have object number 2. And again, mass times velocity. And then we have this plus between them. So it's the total momentum that we started with at the beginning is equal to the momentum at the end. They might change a little bit, and a lot of that has to do with the mass, how much mass each object has, and how fast each object is going. And we could even look at one of these objects might not have any momentum, because if it has a bunch of mass but it's not moving, and in the end it has nothing. We don't worry about it. But so that's kind of the equation here. So let's keep going. I'm going to erase this. Let me go down a little bit. The one thing that's really important to remember about this is direction matters, because you're going to have objects moving perhaps in opposite directions. Now if they're not, like if you have the one ball going this way, the one ball going this way, so they're not moving in the same direction. So if they're on like a surface here and they're moving, so if we were on an XY plane, this was our Y, this is our X, then if something was moving this direction, we might say it's negative, and if it's moving towards this direction, it's towards the positive, it's increasing, so it's positive. And that's really a good way to look at this. So, and this refers to the velocity, because the mass can't be negative, it's going to be positive no matter what. Unless it's in a black hole or something, I guess. But so the velocity, the direction of the velocity matters. So whenever you're doing these problems, make sure that if they're moving opposite directions, that you make one positive, the other one negative. Okay. So let's look at an example here, a problem that will help us understand. Maybe give you an example of how to do one. I'm going to erase this and pull this down. So here we have a 76 kilogram boat. It's initially at rest, so the boat's at rest. And it's a boater. Okay. So the boater is initially at rest in a stationary 45 kilogram boat, steps out of the boat and onto a dock. If the boater moves out of the boat with a velocity of 2.5 meters per second to the right, what is the final velocity of the boat? So what we want to think about here is we have two conditions. So we have mass 1, velocity 1, mass 2, velocity 2. So the mass is important. So this is going to be the boater, 76 kilograms. We'll just put kg. Okay. The boat is 45 kilograms. Okay. And then and then we have 76 kilogram boater initially at rest in a 45 kilogram boat. So velocity initial for this one is 0. And then velocity initial for the boat is 0. Okay, now this is going to be also final, so we'll just make them initial and final, because the boat isn't going to change. Okay, but initially they're both at rest. So then if the boater moves out of the boat with a velocity of 2.5 meters per second to the right, so this is going to be our positive one. So velocity final for this one is going to be 2.5 meters per second. Then it wants to know what's the velocity of the boat. Okay, so we have all this. And so then we can calculate it. So the thing we want to remember here is if we look back at this equation, I'll just go do this real quick. Let me go forward actually. I'm going to try this. Hopefully it's going to work. So if I go back up here, here's the equation we're going to use. It's going to be mv1 initial, m1v1 initial, that's the boater. And they have no velocity, it's 0. And then the boat, m2v1, or v2, what it should be actually. v2 initial is 0 as well. The mass is 45, but there's no velocity, so both of these actually cancel out for this equation. So this side is 0. And then we need to figure out what is the velocity of the boat. So then we plug in mass and velocity, and then we know the mass of this, and then we just have to solve for the final velocity of the boat. So let's plug our numbers in here. Let's move our equation back down here. So these are the numbers we got. Let's write the equation up here. If you remember, the first initial part is 0, so we'll put that in, because neither are moving, the boat or the person. So then if we plug in for the other side, we have the mass of the person, 76. That's going to be times his velocity. He's moving to the right, so he's a positive. 2.5. And then we're going to add the mass of the boat, which is 45. And that's going to be times his velocity. And then we do the math. 76 times 2.5. You get 190. Becomes 190. Plus 45 V. And then we just move this 190 over, so we're going to minus 190 from both sides. We're going to have to move this down here. This will cancel. And then that's going to be equal 0, but then we're going to have minus 190 on this side. You might say, on negative, how's that going to work? I'll show you in a minute. Okay, so then this all comes down here. We end up with, just put some arrows here. We end up with negative 190 equals 45V. And then that's just a positive, won't worry about that. And then we just divide both sides by 45. And we use our trusty calculator. And we figure out what the answer is. Let's use our calculator. And we'll go to this thing here. 190 divided by 45. 4.2. So it's negative 2. Negative 4.2 equals V. So that's the velocity, and you will put the unit on meters per second. And you might say, well, what's the negative? Well, we said that the negative denotes the direction. So the person steps out of the boat to the right. They go this way as the person stepping out. We'll draw a person doing that. And then when he steps off of it, he applies that force of him, you know, and the boat goes this way. So if he steps out at 2.5 meters per second, the boat is going to go in the opposite direction, 4.2 meters per second. And that's an example of how you solve these. Sometimes it'll give you, initial velocities. Sometimes it'll just give you one is standing still, the other one's moving. You just plug in as needed. Sometimes it'll be 0 on this side because this time it was. I mean, imagine it. Neither one are moving initially, but then eventually one moves, causing the other to move a different direction. And that's kind of an example of how you solve these. So you're ready to do the next practice set. Once you've watched these notes, try them out. If you think you can do them, just go ahead and do them. If you want to wait till class and have me help you with them, that's good too. Hopefully that helps, makes sense to you, and see you tomorrow.